Hello, this is our group midterms practical test. Essentially what we had to do, we had to make a circuit that involved a 555 timer that has a variable oscillating sourcing output to drive the coil of a relay used to isolate and control the on and off states of two LEDs connected to a Wheatstone bridge to sense light intensity, providing adaptive brightness for the flasher circuit. So in short, what it wants is sequentially triggering LEDs that adapt the brightness depending on light. And this is a diagram that shows it how it effectively works. You have your 555 timer. It's essentially what causes the 555 timer to time at a specific rate is like the total capacitance times the total resistance, and that gets us 1.1 seconds in this case. And this results in it lighting up the output every so often. And that, as a result, let me pause it for a second. Alright, so whenever this 555 timer goes off, it powers up a relay. And the relay has a direct power connection with a 470 ohm resistor on it. And then that causes it to switch these two lines every time it's pulsed by the timer. And as a result, each line goes into a Wheatstone bridge. Now, we use a Wheatstone bridge. It involves a photoresistor on each one as well as a potentiometer. The potentiometer is effectively a dial resistor. You can dial up the resistance, dial down the resistance. And what we did is that we imbalanced the ohms, the total resistance on each side, to make the current go through this LED as much as possible rather than just going through these two grounds. In this case, we wanted it to be fully bright when there was good ambient light and then be dim when it's dark. And these photoresistors, resistance kicks up when it's dark, lowers when it's light. So after some fiddling, we got it how it works as displayed. Now let's go into some calculations. Showed you the time constant, the total resistance times total capacitance gets you the time in seconds. The next would be the voltage drop for the capacitor. This is 900 microamps. Yes, microamps. This is 900 microamps when you overall current wise. So you take the 900 microamps times it by 1,000. That gets you 0.9 volts voltage drop. Do the same thing for this, 9 volts voltage drop. And finally, with the capacitor, when the capacitor is fully charged, it completely drops the current to 0. Finally, we have the circuit in question. It's probably hard. It might be hard to clearly see, but that's why we showed the diagram earlier. But essentially, this is proof that it works. The LEDs are going off in a sequential manner. They're very bright when the ambient light is bright. But if I was to put down well, yeah, about here. It's a little finicky. But if you put it down And here, to simulate it getting dark, you can tell the amber LEDs went down. And roughly the same thing happens with the red lights. That's proof of that. And I believe that is it.